also with our collaborators at DESY, Thomas Biketter and Geert Berglen. This work resulted in a publication that goes under the title Fate of the Electroweak Symmetry in the Early Universe, Non-Restoration and Trapped Vacua in the two-Higgs-doublet Model. And this is overall, it doesn't work.
Did I do anything wrong here?
Maybe I have to point.
No. Try again.
Yeah, and this is overall example of the fruitful combination of collider phenomenology and cosmology. In a nutshell, I will tell you in a few sentences what we did in this work. So we explored the two-Higgs-doublet model, which enlarges the Higgs sector of the standard model with an additional doublet energy singlet. And we explored the parameter space that features a first-order electroweak phase transition. And surprisingly, we discovered interesting phenomena within this parameter space that lead to a non-usual cosmological evolution, namely electroweak symmetry non-restoration at high temperatures and vacuum trapping. And it is interesting that these phenomena, they are most probably present in other multi-Higgs models. So it is not bound to the special structure of the Higgs sector of the next to two-Higgs-doublet model. Another remark is that the effect of vacuum trapping hasn't been always handled well in the literature, and it has often led to misleading specifications of the physical parameter space in many studies. Okay, so as I said, we are interested in the first order electroweak transition, but also in other financial temperature effects that might be relevant during the electroweak cosmological epoch. And to put a bit of context, the first order electroweak transition would have happened at about 10 to the minus 11 seconds after the Big Bang. And this phenomenon has been extensively studied in the literature. And why is it so popular, and why is it worth studying such a thing? Well, there are many reasons, but among others, the first order electroweak phase transition, it is required to explain the matter-antimatter asymmetry of the universe via the mechanism of electroweak baryogenesis. It also leads to gravitational wave predictions that could be detectable by experiments that are already projected for construction, such as LISA. And also it requires physics around the electroweak scale that could be proved at present and future colliders. So it seems that it is central to understand what a first order electroweak phase transition is in order to understand what we did in this project. So I'll give here a little reminder. In the framework of finite temperature field theory, the scalar potential develops a part at higher loop orders that depends explicitly on the temperature. And this part is responsible for the restoration of the electroweak symmetry at high temperature. So the vacuum configuration sits here at the minimum at the origin of field space. And as temperature decreases, another minimum starts to be formed and eventually becomes degenerate with the minimum at the origin. And they are both separated by an energy barrier. This degeneracy happens at a critical temperature. And as temperature continues to decrease, the minimum at the origin becomes metastable, and then a first order electroweak phase transition can be triggered via quantum tunneling or thermal jump. And this is when the electroweak symmetry breaks. Okay, and why studying the first order electroweak phase transition in multi-Higgs models? As you know, baryogenesis requires three conditions to be accomplished. We need baryon number violation, we need CP violation, and we need a situation of departure from thermal equilibrium. And this is what the first order electroweak phase transition is providing. Intuitively, if we have baryon and CP violating process A plus B, if this process is in thermal equilibrium, there will be an inverse reaction that washes out the potential baryon asymmetry that we could have generated. So we need to fall out of equilibrium. And the standard model does not feature such a transition because the mass of the Higgs is too heavy for it. And this has often used as the need for beyond the standard model physics. And extended Higgs sectors are a popular choice that could accommodate this phenomenon. And it's a very active field. There are many studies in singlet extensions, doublet extensions, or as we do here, doublets plus trial singlet extension. So the model, the next to two-Higgs-doublet model. And the two lines of the three-level scalar potential is just the usual CP conserving two-Higgs-doublet model with a set 2 symmetry that prevents the existence of flavor-changing neutral currents at 3 level. And the third line is just the line that contains the terms that involve the singlet field, and that it's actually invariant and under an extra set 2 symmetry that flips the sign of the singlet. Here we have 3 fields that are allowed to acquire a vacuum expectation value, and when this happens, and after spontaneous symmetry breaking, we are left with 6 physical scalars. So we have 3 CP1 scalars, for which one of them is the 125 GeV that has to account for all the measured properties of the 125 boson within the experimental uncertainty. Then there is one CP0 pseudoscalar, 2 charged scalars, and in this study we are interested in exploring the Yukawa type 2. And the next to two-Higgs-doublet model has a huge parameter space. It has 12 free parameters, so we have to constrain them under various theoretical and experimental requirements. For example, among the theoretical requirements, we want to ensure that our theory can be treated perturbatively. So we have to constrain the eigenvalues of the scattering matrix of processes to 2 scalars in the high energy limit. And also, to ensure the stability of the vacuum, we need a potential that is bounded from below. And for example, we might have also an electroweak minimum that is metastable. So we have to be sure that it is compatible with the age of the universe. And then among the experimental constraints, our parameter points have to be in agreement with measurements of electroweak the formalism of the oblique parameters ST and U. Also, we have to account for measurements of flavor observables and to accommodate recent searches for additional scalar states and the measurements of the properties of the 125 GeV Higgs boson. Now, the one-loop effective potential. At 0 temperature, quantum corrections can be incorporated into the potential by the well-known Coleman-Weinberg potential. But at finite temperature, at one loop, we need an extra piece that depends explicitly on the temperature. But this is not the full story, because it is well known that finite temperature field theory, there is the breakdown of perturbation theory. And there is a set of diagrams that are called the DESY diagrams, and they look like this, whose contribution we cannot neglige at high temperature. So they have to be resummed and included into our potential in order to perform reliable calculations. And this is the expression that we have to include. Okay, now I will tell you how to hook up first order electroweak phase transition in two-Higgs-doublet models. This is a well-studied scenario that we can use as an anchor as a starting point to study the next to two-Higgs-doublet model. So first we need an energy barrier. This could be generated by three-level effects, but this is not possible in the two-Higgs-doublet model because there is a set 2 symmetry that forbids odd powers of the fields that would generate the barrier. So necessarily the energy barrier must come from radiative and thermal corrections in this kind of models. And as a toy example, in a theory with a Higgs that has a mass that has a term coming from bilinears, terms in the potential, and another term proportional to the fields and the quartic couplings. In the thermal potential, we will have a term that looks like this. In this big pi stands for the thermal mass. So when you have large quartic couplings, this term will be relevant over the bilinear piece or the thermal mass. And then we will effectively generate a term here that is cubic in the fields, and we can have the energy barrier. So we need large quartic couplings, but this is translated into that we need large splittings between the scalar masses and or between these masses and the overall mass scale of the soft breaking term divided by sine beta cosine beta. The second step is that we have to make this scenario of large splittings compatible with experimental and theoretical constraints. So we will regard that the mass of the pseudo-scalar, that the mass difference between the pseudo-scalar and the CP even Higgs is larger than the VEV, than the electroweak VEV, and also that the big M, capital M, is more or less also equal to the VEV. Yeah, to the electroweak VEV. To take into account electroimprecision observables, we will set the mass of the pseudoscalar to be equal to the mass of the charge Higgs. And also to take into account flavor observables, which constrain the plane of tan beta and the mass of the charge Higgs, we have to take into account that it has to be larger than 600 GeV, more or less. Also, low tangent beta values favor baryogenesis. And this scenario of large mass splittings has a smoking gun process. That is the decay of the pseudoscalar into a Z boson and the CP even additional Higgs. So in conclusion, for the two-Higgs-doublet model, we need large splitting between the scalar masses and or between these masses and the overall mass scale of the second doublet. But also the mass spectrum in the Yukawa type 2 is more or less fixed by all these constraints that I was talking about. So for the next two-Higgs-doublet model, we also need large splittings because we also have the Z2 symmetry softly broken. And we have 12 free parameters. So our strategy will be to fix the parameters that are common to the two-Higgs-doublet model and the N2-Higgs-doublet model in such a way as we would want to have a first order electroweak phase transition in the two-Higgs-doublet model. Related to the singlet field. So we change the mass of one of the CP even Higgses, its singlet components, and the value of the singlet VEV. And yeah, and we will be also working in the alignment limit. Now, vacuum trapping. What do we mean by vacuum trapping, and how does this change the picture of unusual first order electroweak phase transition? So as I said, at high temperature, the electroweak symmetry is restored, and as temperature decreases, the other minimum forms, and there is a energy barrier that separates both minima. But it could happen that the transition probability is not big enough for the transition to take place, and then the universe remains trapped at the false. So this is leading to an unphysical situation. Yeah. To explore this effect, what we did is to explore the parameter space that I showed before. And here I'm showing the singlet component of one of the CP even Higgs bosons in dependence with its mass. And the color coding indicates the critical temperature that I remind you that it was the temperature at which both minima are degenerate. I also remind you that we have 3 CP even Higgs bosons and then they mix in this model. There are numerous studies that regard the existence of a critical temperature as a sufficient condition for the transition to take place. So according to these results, a large part of this explored parameter space would indicate that we have a first order electroweak phase transition. However, when we compute the actual transition probability and the transition temperature, we see that there are many points that do not feature a transition temperature. And those points remain trapped at the origin at zero temperature, and they are unphysical. So we remark here the importance of computing the transition probability and the transition temperature, even though it is a bit more involved than computing just the critical temperature. And now a bit on the collider side. yeah, in the two-Higgs-doublet model, but also in the N2-Higgs-doublet model, this coupling vanishes in the alignment limit. However, we have two channels here allowed, that is the decay of the pseudoscalar into a set and one of the CP events, and also into the other CP event. And yeah, and we see here that smaller transition temperatures or a stronger first order electroweak phase transitions are related with larger values for these cross sections here. And again, not taking into account the black points, so the trapping would lead to misleading prospects to find these new states in colliders. And in our paper, we propose this search that hasn't been done because we are exploring a regime of a low tangent beta. And there is, however, a search into BB bar. And we also have quite heavy states here. So this could have good prospects to find this kind of scenarios. And now the other part of the study is about electroweak symmetry and restoration. Commonly taken for granted image is that the electroweak symmetry restores at sufficiently large temperatures. And this is not always the case. Yeah, what do we mean by high temperature? So we studied here a regime in which the temperatures are larger than the bilinear terms of the theory. But also, as I said before, we are exploring a regime of relatively large quartic couplings. So we will explore temperatures for energies at which the theory still remains perturbative. So this is what high temperatures means for us in this study. And here there is again the same plot that I showed before. And we can distinguish three qualitatively different regions. In this plot here, I'm showing the electroweak bed dependence with temperature. And for example, for the trapped points that I explained before, we see here that at 0 temperature, the web is equal to 0, so it's not physical. But as temperature increases, we find that here the electroweak symmetry breaks. And yeah, it continues like this up to the TeV scale. For the colorful points, what we have here is that we have a first order electroweak phase transition at about 200 GeV. At larger temperatures, the electroweak symmetry is restored, but then it breaks again at 600 GeV. And for the gray points, the electroweak symmetry is never restored. And now we would like to have a way to assess in which regions of this parameter space we can find this particular effect of electroweak symmetry non-restoration. And to do so, the one loop effective potential can be handled analytically in the high temperature limit. Is unstable in a given so under certain conditions, outside the origin of field space, because I remind you that we have 3 fields, and still the electroweak symmetry could also be restored at a point where the value of the singlet field is non-zero. So for the same plane, again, we have here the values of the 3 coefficients. A blue value indicates a negative coefficient and a red value is a positive. So here we feature in this plane all negative values of C11, which indicates that all these points are featuring electroweak symmetry non-restoration at high temperatures. Yeah. And
sorry, can you remind me what the open circuits?
yeah, these are the points that also feature first order electroweak.
These were the colorful points.
Yeah. Okay. Yeah. And well, this is pretty much what I wanted to tell you today. Yeah, so there is interesting phenomena that can take place in multi-Higgs models that in the regime of large quartic couplings that also feature first order electroweak phase transition. The coefficients can easily identify points in the next to two-Higgs-doublet model where the electroweak symmetry is broken at high T. So if we are interested in a particular cosmological history, we can easily use them to identify these regions. And also the finite temperature analysis and the calculation of the transition temperature are actually needed and very important to correctly identify the physical regions of the parameter space. Yeah. Thank you.
Thanks a lot. I have to admit, when I saw the talk, I was sure you would be talking for an hour. And, but I'm also sure that nobody really minds because we have many talks here and then we have a little bit more free time. Olalla. Yeah.
So you showed at some point that you took into account these electroweak precision observables, right? And there was a relation between the masses of some of the scalars.
Mm-hmm.
So does it mean that only, because I think it was that some of the charts need to be equal to some of the pseudo-scalar states that you have. So you evade these values only if they are exactly equal? Is there some tolerance, or is this somehow a killing?
No. I was talking here of a particular scenario, of a typical scenario where you have a first order electroweak phase transition in a two-Higgs-doublet model. And this is one of the scans that we do in our publication. But we do also additional scans. And for that, we take in a more, we use the formalism of the STU parameters to not have exactly the mass of the pseudoscalar equal to the mass of.
There was one more question.
So your idea is that if you have symmetry non-restoration at the high temperature, then you could have a first order first transition. Is that the idea?
So in the points that we analyzed, you can have first order electroweak phase transition here, and then the electroweak symmetry breaks again. So they both can happen within the same cosmological history of the same parameter space point.
And what would be the phenomenological smoking gun of this kind of scenario?
Of the electroweak symmetry non-restoration, that would be
for colliders.
Well, related to So as we said, it's typical to have large splittings between the scalar masses, to have large quartic couplings, and then to have first order electroweak phase transition, or also symmetry non-restoration. So where was this? Yeah. So this will be the process that we were studying. Well, actually, this will be the smoking gun signal, because you have a large separation between the mass of the pseudoscalar and the mass of the CP even Higgses.
Yeah.
Is there any parameter space where you have first order phase transition from symmetry non-restoration to symmetry restoration? Parameter point where first order phase transition happens, even for
you mean kind of an inverse transition from
transition.
Symmetry non-restoration to restoration?
Yeah, in the previous talk, I think that the transition is not first order because the line is smooth.
Yeah. Actually, we did not find such a situation.
Okay, so in this model, you didn't find any.
Yeah,
parameter.
But we also didn't explore all the parameter space. Yeah, with 12 parameters, it's complicated. But it's an interesting question, of course.
And then if that happens, that can be a smoking gun signal in terms of gravitational waves, because you have double transition.
Yeah.
Quantum.
Yeah.
In all, well, when we were starting all this, we were also thinking always of gravitational waves. Only that this was kind of postponed to the second project because we found already enough material in this part here. And you would expect the gravitational waves strongest, of course, here where the yellow points are. Yeah, where the Tn is smallest. And then unfortunately, what Olalla found was that many of these points where we would naively probably expect a large gravitational wave, they're excluded. Yeah? So makes the possibilities for gravitational waves a bit more complicated.
Yeah, usually also what we've seen in many studies is that one uses the strength of the transition, which is the critical depth divided by the critical temperature, as a way to assess the successful variogenesis and so on. And when you do that, you could conclude that here you have a very large strength for the transition. But then when you go and actually compute the transition temperature here, you don't have a physical situation. Yeah.
More questions or comments? Well, then, thanks again.
I had a question.
25 minutes that we spent. Okay.